Questions? 5, 6, fine. Good, let's do it. Okay, let me pull it up here. 5, 6, 41B. Yes. Do a classroom. Come on, come on, come on. Cactus, do a classroom. Come on. Sometimes. (41B). Oh, yay. Okay. Verify each identity. The arctangent of x plus the arctangent of 1 over x is equal to pi over 2 for all x greater than 0. All right. Harpy. So we talked last time about some ways that I typically approach these kinds of problems. I can apply them with a picture. I can apply them with a standard conversion where I try to convert arctangent into something. Either one of those is okay for this problem. I'm going to start by looking at the picture version to see how it works, and then I'll see how it fits into this picture. So let's start off with, I'm going to need two pictures. One picture that's going to represent arctangent of 1 over x, and one that's going to represent arctangent of x. See what happens when I put those two together. Now, how I put these two together is going to be pretty neat whenever I get done, so take a look. Sometimes with the picture version, if you're not creative with how you use it, it's not helpful. That's just the nicest way I can say that. Occasionally when you try the picture version, it is just not helpful unless you are very creative with it. So let's take a look. I have the first piece, I'm going to call that theta 1, which comes from arctangent of x. So I'm going to use arctangent of x to create this triangle. I'm going to use arctangent of 1 over x to create this other triangle with theta 2, as I'm going to call it. The reason I have to use different thetas is I don't know if the angles are the same. And in fact, in most cases, they probably aren't going to be. So let's try this out. This first one, if I'm doing tangent of x, remember that it's tangent of x over 1. And arctangent, as a reminder, arctangent comes from the tangent function. This means that tangent of theta 1 would be equal to x over 1, which is a reminder, tangent is opposite over adjacent. So this means that my side over here is x, my side over here is 1. The second one, as a reminder, arctangent is the equivalent version of tangent of theta 2, where in this case tangent of theta 2 is 1 over x. Again, that's opposite over adjacent, so that'd be 1 over x. Why is this so important? When we look at these two pictures, they're the same picture, just from different perspectives. In this case, theta 2 is actually also in my first picture. Theta 2 is right there. That's kind of hard to see. Theta 2 is also right there. Why is that so important? Because the question asks us about what happens when I take arctangent of x plus arctangent of x over 1. Well, as a reminder, arctangent of x I have defined as theta 1. Arctangent of 1 over x I have defined as theta 2. If we look at this picture, theta 1 plus theta 2 plus 90 should always equal 180. The triangle angle sum theorem from geometry. I can then subtract 90 from both sides. I get theta 1 plus theta 2 is equal to 90 degrees. And if I convert this into radians, I would get theta 1 plus theta 2 is equal to pi over 2. Which is exactly what the problem asks us to show. So this is where I have to use the picture version. I have to first recognize that the two pictures are related to each other, see then how those pictures are related to each other. They're the same picture, just from different perspectives. So in this picture, theta 2 is down here, theta 1 would be up there. They're the same basic picture. These are referred to in geometry as complementary angles. And this is always the case. So this is the picture version. Now if I want to do it by a formula version, this takes a little bit more work. It is possible, but it's going to be very similar to how we approached it here, but without the picture to help us. So again, I have to look at it and say, how can I find these two pieces and how they fit together? So let's try this version without the picture. This time I have the original equation, which was arctangent of x plus arctangent of 1 over x. And I want to prove that this is equal to pi over 2. Okay, so this problem, one of the things I want to look at is I want to see if there's any connection between, say, for example, my formulas from geometry or my formulas from trig. So I might pull out my trig cheat sheet and see, is there some other way to write arctangent in terms of other functions, and see if I can get it to work itself out. So I have this problem. I might turn this into, let's see, this would be the first one, tangent of theta 1 is equal to x over 1. This one becomes tangent of theta 2 is equal to 1 over x. And so what I can do here is I can try to convert these two into some standard function. So in other words, I want to show that if I resubstitute these problems, that theta 1 plus theta 2 has to equal pi over 2 somehow. The best way to show that is, again, via the picture. Let's show that they're related to each other. Without the picture, my best bet is to try to form another trig relationship like with sine or cosine and try to force the two to work itself out. Doing it without a picture is incredibly difficult for this problem, at least with the standard trig techniques. Alternatively, I might look to see if there's like a way to look in my arctangent formulas and see if there's a way to rewrite tangent of 1 over x. Maybe there's some formula that rewrites tangent of 1 over x as something else. And maybe that gets me closer. But without those pieces, the picture is by far the best way, even though the picture is not an easy way to do this problem. So I recommend this approach, but it requires some creativity, some geometry skill, versus the other one where I have to rely upon a formula that I may or may not remember at all. In this case, I don't remember it, so I'm either stuck or I'm going to have to do some research. So that's what I do on 41. I do the picture version, show them the same triangle from different perspectives, they use the triangle angle sum theorem, and solve. Other questions? This was from question 41B from section 5.6. Other questions? Well, I got a moment. I guess I should follow through on my promise. Let's see if there's a formula that lets me rewrite it. I will stop researching when somebody says they have a different question. Let's see. What is this? Arctan alternate formulas. Or, you know what? fancy word I'm not using quickly. Arctan densities. Oh, looky there. Ooh, that looks promising. So I could try to convert. Still pixelated. Mine. I could try to use this conversion. It's a trig identity. Apparently, there's more than one of them. To try to convert this into a different version of arctan and see if this gets any better. I imagine I would probably do this on the 1 over x version, and then try to algebraically simplify it as far as I physically could until it figures itself out. But without those pieces, like, you think I got that formula memorized? Like, no, I don't. Without those pieces, I'd have a difficult time trying to do this without a picture. So I went straight to picture. By the way, that comes from my background. I had a strong background in geometry. So I use my best skill to my advantage. If you have a better background in algebra, you may like the other way. Other questions? Do an awkward dance at this? I guess I'll pause until we get a question. All right, let's do 45. So for 45 from section 5.6, we're asked to take the derivative of the following function. In order to do this problem, I want to make sure I have my table out and ready and available. If you plan on taking the AP exam, I would just start learning and memorizing those two tables, the basic integration table and the basic derivative table. I will allow you to use a cheat sheet for our test, but if you plan on taking it, you have a month. I spend some time memorizing. 45. We have g of x is equal to 3 arc cosine of x over 2. Okay, we're asked to take a derivative. I'm going to go back to my cheat sheet. Mine's right here. All right. It says they have arc cosine of u. So first thing I want to recognize, and this is 3, which is a constant, times arc cosine of u, where in this case my u is x over 2. I've not written it in u form, but to do the derivative, I need u prime. So I find u prime. U prime is the derivative of u. The derivative of x over 2 is 1 over 2. So I then plug in my formula. My formula says the derivative with respect to x. So again, I'm taking the derivative with respect to x. And that's what the entire problem would look like if I'm showing every single step of my work. I'd first pull the 3 out. Remember, I don't need the 3 in my derivative. It's just a constant. It gets pulled out. I would then use the rule formula. The formula states I'd have 3 times, my formula is negative u prime, so negative 1 over 2 over square root of 1 minus u squared, so x over 2 squared. I then start simplifying what I can into a more simpler function. So in this case, I'm going to pull the negative out. I'm going to pull the 2 forward. This would become negative 3 over 2 square root of 1 minus x squared over 4. So the 2 moves to the bottom, the 3 moves to the top, the negative stays at the top, and then I distribute the square into both pieces. I don't like this version if I'm doing it for like a test for multiple choice. It's probably not the answer I would give. If it was just asking for the derivative, I'd probably be okay and stop here. Alternatives, though, would be to write it as, let's see, I could factor a 1/4 out. If I do that, I get negative 3 over 2 square root of 1/4 times 4 minus x squared. Why on earth would I do that? Well, because the square root of 1/4 is a nice number. The square root of 1/4 is 1/2, and 1/2 and 2 actually end up canceling. So I end up with this equation, negative 3 over the square root of 4 minus x squared. That's my preferred answer. Which I believe is the answer the back is. Right, correct. I'll double check. Now again,
Yes.
all those answers are the exact same, so like, it doesn't matter as much as you think, but at the same time, like, one is better and more likely to be on your test. This is an old trick I used from algebra. I can factor 4 out, but I got to factor 4 out from both pieces. So I factor the 4 out from here, it disappears, leaving x squared. I don't have a 4 here, so I create a 4 by making it 4 over 4. I take the 1/4 out, the 4 on top stays, leaving just 4 minus x squared. It's a pretty nifty trick. Oh, thank you. What you were saying?
Oh, well, I turned it in
Yeah,
the
no.
other day, but I actually didn't mark this down. Yeah.
All right. That was 45. So I used a fancy trick at the end. Normally, I'd leave it right here, but if it's multiple choice, I'd go all the way there. Common mistakes with this one. Not taking the derivative correctly of the u. So instead of getting x over 2, you might try to do like a quotient rule or something really silly. Remember, it's just a constant, so it's just x becomes 1, and the over 2 just stays over 2. And then not distributing a square. A lot of people would put x squared over 2 instead of x squared over 4. Another common mistake. Remember, the square applies to the u, which is both x and the 2. Other questions?
Would you do the same thing for 49?
For 49?
Yeah. Over x squared?
For 49. So for that one, I have to use a quotient rule. So let's do 49. So I'll apply 49 the same way I did 45. I will isolate my pieces in my rules and then apply the derivative to each piece separately. I have in this case the following function, 49. Arc sine of 3x over x. First, I recognize this is a quotient, so I must apply the quotient rule. The quotient rule says I have to have a low piece and a high piece in order to apply the rule. So I identify those. My low piece, that's the high piece. It's going to be one kind of day if I can't identify low and high. So here's my low and my high. So then I look at each derivative separately. So we'd have the low is x, the derivative of low prime would be 1. My high is arc sine of 3x. To do my high prime, I don't want to do arc sine of 3x. I want to do arc sine of u. Because remember, my function, my rule, is assuming there's a u inside. So I'm going to rewrite this as arc sine of u, where my u is 3x. That makes my u prime 3. And I plug into my arc sine formula. My arc sine formula is u prime, so 3 over the square root of 1 minus u squared, so that'd be 3x squared. Or, alternatively, 3 over square root of 1 minus 9x squared. So I now have my four pieces. I have my low, low prime, high, and high prime. I then plug into the quotient rule. The quotient rule says to find the derivative of this function, the derivative with respect to x of arc sine of 3x over x. This is going to be equal to, big fraction, low x d high, so that's 3 over square root of 1 minus 9x squared, minus high arc sine of 3x, d low, which is 1 over the square of what's below, x squared. For this problem, I would not simplify a lot. I'd combine these two together to get 3x over the square root of 1 minus 9x squared minus arc sine of 3x all over x squared. But then I'm probably just going to stop. I don't think the book went much farther. It might have gotten rid of the radical denominator, but not much. Feel free to double check that. If it did, so I'll preface that just in case it did, my solution would be 3x minus arc sine of 3x times the square root of 1 minus 9x squared all over x squared, square root of 1 minus 9x squared. Which I hate more, because now instead of having a fraction instead of a fraction, I have a radical in the denominator still. And so I'm like, do I have to fix that one too? And it's like, stop already. That's why I'm the king of stopping already. Let the trig student figure that one out. Let the algebra student try to scramble their brains. Okay, that was number 49. So let's see these getting questions answered today. Wait, everybody else is okay. Any other questions? Michael's like, nah, two.
Yeah, my brain's not working. Can you do 9 on 5.7?
Yeah.
Explain I want to work with now, if you want to take it to work with instead of the intervals.
Okay. I'm going to use this cheat sheet 9 times out of 10. So
Oh,
let's go to number 9, you said? Am I good to erase number 49 up here? Hearing no objections. Number 9? All right. Number 9. Number 9 states, I have the integral of t over the square root of 1 minus t to the 4th dt. So before I begin, I want to recognize which version of this formula is most likely. I have a square root with subtraction inside of it in the denominator. So I go to my list. I'm looking for one that has a square root with a subtraction inside of it. In this case, my variable is on the right-hand side. So this is looking a lot like number 18, right here, the arc sine initiative. So let's write down what that says. It says the integral of du over the square root of a squared minus u squared is equal to arc sine of u over a plus c. So if I can find a way to write this in this specific u and a form, I can do this derivative. So for this problem, I need to pick a u such that this statement becomes true. Let's pick my u. Do so. I want to make my u t squared. Now, there are two reasons for me to do this. Take a gander here, guys. Number 9. There are two reasons to choose my u is equal to t squared. Number 1, this actually makes my original formula work very nicely. Because if my u is t squared, then the reason why this is t to the 4th is because it's t squared squared. So that part checks out. The second reason is I need du in the problem. And du is 2t dt. Well, I don't have 2t dt, but I have t dt. So that tells me that I'm really close to having the correct solution. I take this formula, I divide both sides by 2. I end up with I don't know what's going on outside. I'm not sure I want to know. So there we go. I have my problem, t dt. That t dt will be replaced by 1/2 du. I've got my u equal to t squared. And the last thing is, if I want to use this formula, I also need to have a. So I'm going to make my a 1. I pulled that from the problem itself, because if I wanted to match the a squared, well, 1 squared is 1, so I know that works. Common tricks you can do if you're having trouble figuring out what to use as your u and using as your a. Very common tricks is just pull the two pieces out. I want these two pieces to match, so make them match. And solve. I take the square root of both sides to get 1. I want these two pieces to match, so make them match. And then I need a in order to do the problem, so I take the square root of both sides. I get u equals t squared. I get a equals 1. Now I can start my problem. It's a trick, but it's a logical trick. Now from here, I plug everything in, and I get to my solution. So first, this becomes the integral of, so remember, I have 1/2 du replacing dt, so this becomes 1/2 du over the square root of 1 squared minus u squared. I pull the 1/2 up front, getting it out of the way so I can apply the rule easier. And then I write down my parts. 1/2, still up front. This becomes arc sine of, on top goes my u. My u is t squared. On bottom goes my a, which is 1 plus c. This is my solution, is 1/2 arc sine of t squared plus c.
Yeah, I realized what to do once you said use substitution. I was like, right, that's the rule that we have.
I can't stress this enough. The reason these are in u form is because it assumes everything is u substitution. That is why. And so what I will do is I will treat every single problem as a u substitution problem, which actually makes it easier. Because rather than memorizing the u substitution and all the formulas, you just do them both at the same time. And so there's only one formula memorized for both pieces. I'll take your word for it. Other questions?
My body does not like that.
It's terrible.
I like it, but my body doesn't.
Why is it salty?
I have no idea, but my dad, anytime he would make anything, if he puts salt on it, I swear, rather than just sprinkling it over to like enhance the flavor, he would, I swear what he would do, to taste like this. He would take it, unscrew the top, don't. It was like, alright, 1A, don't.
I was going to let you know. If salt enhances the flavor, what happens when you put salt on top of salt? Does it make the salt stronger?
Yes.
I think so.
Because like,
So how much salt becomes spicy salt?
like my
Is that where we die? Because it's too spicy?
like my question is, like, why does it taste like you just took a freaking thing of salt, put it in a pan, and like, alright, that's better. You want less blood pressure, so like, and then but that's why that didn't affect salt wise.
It's also probably why it hurt me the most. Because I don't eat salt.
No, because you have to use spices.
Spicy is delicious.
Yes.
No.
Might make some curry tonight.
That sounds good.
You wanna bring me some curry?
Heck no.
Or if I just come to your house?
That would be awkward.
Yeah, but
You ever made barbecued curry?
No, I've never had curry period.
You make a. So I make my own barbecue sauce.
Uh-huh.
You use a ketchup base for most St. Louis and Kansas City sauce. And you mix spices, Worcestershire, and other things into it. And it makes barbecue sauce. Fun facts. Barbecue sauce, fancy ketchup.
Mm.
But if you mix it, and the spices are curry spices, don't add sugar. It ruins the flavor.
Can I just show up to your house with mozzarella sticks for curry?
No. Sorry. Monty sticks are great. But curry. Curry is life.
You sound like Ron Lee. It's the curry of life. It's so spicy and flopping back to life.
Other questions? Besides my creative life, apparently. Just Wednesday.
It's so hot in here.
I'll talk about it. This is not sweat.
Oh, dude, I've been sweating. And I know it's solely because of citric acid.
They're just like, let's not turn on the AC. I'm like,
It wasn't hot in the leg room, and it's always cold in there. And I had it at 68, and it's so hot in there.
see, weight rooms should be cold. Because when weight rooms get warm, there's no fixing it.
Yeah.
It just becomes a sauna. No one wants to be that person. Which one not? I got nothing to do up here, man. I'll do a whole problem.
Derivative of power.
What you got? What's the extra problem?
5 to the negative 4.
And we're taking a derivative?
Yeah.
Okay. So this would be d dx. Okay, so as a reminder, I'm going to do this in u form. Okay? Which means I'm going to force the power to be a u, find du, and then use my cheat sheet formula. Okay? Ready? So first, what's my u? Well, my u is going to be negative 4x. So that means my du, or the derivative with respect to x, we also call u prime sometimes, the derivative of negative 4x would be negative 4. The question becomes, what is the derivative with respect to x of 5 to the u power? Well, if I go back to my cheat sheet for derivatives, where you at? U is right here. Okay. I see number 12. Number 12 says the derivative with respect to x with an a base and a u power. So my a in this case would be 5, and my u is, of course, u. It says this is equal to ln of a, so that'd be ln of 5 times 5 to the u power times u prime, or du dx. I just plug everything in. ln of 5 is ln of 5. 5 to the u power will be 5 to the negative 4x times u prime, which is negative 4. I then just use order of operations to move the negative 4 up front. Negative 4 ln of 5 times 5 to negative 4x. That's my solution. So notice that I first put it in the form my sheets want to use, right? It's in U form. So once I have it in U form, I then copy the U form over, and then it's just a plug and chug. I have my derivative, I have my U, there's my formula, and then the rest is just making sure to write it algebraically correct. So putting the negative 4 out front. And not doing silly things. The number of times I've done a problem like this, started talking to a friend of mine, come back to the problem and be like, oh, minus 4, and thought it was subtracting 4, instead of being a times a negative 4. The number of times I've done that, too high. Too high. It's silly algebraic mistakes. 5 minutes. Any other questions? Stealing my cheat sheet, I see. If we need another cheat sheet, I can print it out.
I just do it at home. It's on my desk.
Any others? 71? Of which section? 5-4? Sure. Let me pull up 5-4. That you already have in front of you.
Yep.
Okay. Give you a moment.
X. Plus y into x equals 1.
We did this one in class. Yeah, but I'll do it anyways. Ready? And it's at the point 1, 0, right?
0, 1.
0, 1. Okay. So first, let's take a derivative. So I'm going to do this in 2 separate pieces. I have to do this with implicit differentiation because you'll notice that in this problem, there is a y intermixed with the x's. So I have to do it by implicit. So what I'm going to do, I'm going to do this problem in 2 separate stages. I'm going to do this piece over here and follow its rules and pieces all the way to the end. I'll then do this piece separately. I will then add them together and make it equal, well, in this case, that's easy, 0. So let's do it one piece at a time. I start with the left-hand piece. Left-hand piece is a product. Because it's a product, I have to apply the product rule. So I'm going to go over here and start my product rule. My product rule states I have a left and a right. My left is x. My right, e to the y. So my left prime is 1. My right prime is e to the y times y prime. As a reminder, if there is a y in your function, you take the standard derivative and then multiply it by y prime. So, there are my pieces. Let's plug them in. To do the product rule, I do left d right plus right d left. So left, x, d right, e to the y times y prime, plus right, e to the y, d left, 1. So that is the first piece. Left d right plus right d left. Plus the second piece. Now for my second piece, I have different pieces. But it's still a product, so I'm going to do the same basic format, left and right. My left piece is y. My right piece is e to the x. Which means my left prime is y prime. My right piece prime is e to the x. So let's take a derivative. I again do left d right plus right d left. So left d right plus right d left. And that's going to equal 0. Now the only big trick in this problem is that I have to get y prime by itself. So now this becomes a very strict algebra problem. I'll walk that step very quickly. So first I'm going to simplify this down to the easiest thing I can. X e to the y, y prime plus e to the y plus y e to the x plus e to the x y prime equals 0. All I did was drop the parentheses and multiply them out. I see all the pieces that have y prime in them. This piece is y prime. This piece is y prime. I want to get those together so I can factor the y prime out and then get the y prime by itself. Common algebraic trick. So what I do is I move the other pieces over. E to the y, move over. Y e to the x, move over. This becomes x e to the y prime plus e to the x, y prime equals negative e to the y minus y e to the x. Then I'll factor y prime out. I get y prime times x e to the y plus e to the x equals negative e to the y minus y e to the x. I then divide it over to get y prime by itself. So y prime is equal to negative e to the y minus y e to the x over x e to the y plus e to the x. That is my derivative. And plug it in and do the tangent line formula. As a reminder, tomorrow we review. Is the sky getting real low?